Welcome back, guys, to another exciting JLand Bio video. Today, our focus is going to be on something called Le Chatelier's principle. So we talked previously about equilibrium and how equilibrium results in the rate of the forward reaction being the same as the rate of the reverse reaction. Well, how do we alter where equilibrium lies? Think about that again in terms of K. If K is greater than 1, then equilibrium lies closer to our products. And if equilibrium if our value for K is less than 1, then equilibrium lies closer to our reactants. So how do we shift the value for K? How do we push equilibrium? And how do things respond when we try to shift equilibrium? So hopefully by the end of this video, you will be able to explain how changes in conditions affect equilibrium, as well as predict direction shifts in equilibrium using concepts related to Le Chatelier's principle. That's our only vocab term for today, Le Chatelier's principle. This is also the last part of the unit. And so after that, we will move on to acids and bases. So if we remember correctly, not all reactions go to completion. We talked about that last time. So what can we do about it to push the reaction one direction or another? And when we do this, we can adjust moles, we can adjust temperature, we can adjust pressure, and that shifts equilibrium certain directions. So if we take a look here, in this reaction of hydrogen, nitrogen, and ammonia. So hydrogen reacts with nitrogen to produce ammonia. When I add hydrogen, notice that the hydrogen immediately gets used up. We add a little bit of hydrogen in there, and then it immediately gets used up. And nitrogen, when that happens, goes down as well. But notice what happens to ammonia. Ammonia increases. So as you can see here, by adding moles or adjusting temperature and pressure, we can shift the equilibrium in a certain direction. The Le Chatelier's principle states that if you disturb a reaction in equilibrium, it will react by shifting it in a balance to undo the disturbance. So if we disturb something at equilibrium, then the reaction is going to go whatever direction it needs to in order to reestablish equilibrium. It likes to be at equilibrium. It's happy there. It's thermodynamically favorable. So if we disturb the system, then the reaction is going to react in a way where it reestablishes equilibrium. So if we add more reactant or product to a reaction at equilibrium, it is no longer at equilibrium, and then the reaction shifts one direction or another in order to be able to reestablish that. And that's what we're going to look at today. We need to be able to determine which direction equilibrium is going to shift when we do certain things to a reaction. And again, there are really three ways we want to look at this. The first one is moles. So by adding more reactant, equilibrium shifts to make more product. If you think about it, it kind of makes sense. When we're at equilibrium, we're rates are equal. If I add more reactant, that takes equilibrium out of balance, and it would make sense that it would shift to the right. It's going to shift to produce more product. That way, it is balanced again. By adding more product, equilibrium shifts to make more reactant. So if I add more COCl2, then equilibrium shifts to make more reactant. So if we take a look at the diagram here, when we added CO, so we added a reactant, notice what happened to the COCl2. It went up. That's because when we add more CO, we end up producing more product. Again, we're looking at the rate here. We're looking at how the rate changes. When I added COCl, notice what happened. The COCl instantly got used, and then we started producing more CO and more Cl over time. Okay, so it's really important that you take a look at this and kind of understand what's going on here. Also, removing the substance has an opposite effect. So if I move reactant, product is going to produce more reactant. So equilibrium is going to shift to the left. If I remove product, then equilibrium shifts to the product side. So by adding it, it goes the opposite direction, and if you remove it, it goes the direction in which you moved it. Temperature. This one's a little bit tricky. Remember that energy is released with an exothermic reaction, energy is absorbed with an endothermic reaction. So for this, we want to consider energy as a reactant if the reaction is endothermic, and energy is a product if it is exothermic. So when we put energy into a reaction, you can think of it as a reactant. So if a reaction is endothermic, then heat behaves as a reactant. If it is exothermic, heat is being released. So we can think of heat as a product. If I take a look at the reaction on the right here, we have a delta H. You can think of that like delta E is negative 57. If it's negative, that means that energy is released. So I think of heat as a product in that reaction. Now we treat heat as temperature, and it works the same way with moles. So for example here, if I look at the reaction on the left, or I'm sorry, on the reaction on the right, we know that it is exothermic. as it releases heat. So we put heat on the product side. Now we just do the same thing we do with moles. So if I increase the temperature, heat goes up, right? So if heat goes up, then equilibrium is going to shift to the left. And if we decrease heat, then equilibrium is going to shift to the right. It behaves the same way as we do with moles, okay? Let's move on. Pressure. So pressure is unique because if we increase the pressure, this shifts equilibrium towards the direction with the smaller number of moles. So if I look at the equation on the right here, I have 4 moles of gas on the left, 2 on the right. So if I increase pressure, that means that equilibrium is going to shift towards the lower number of moles, which is on the right side. So if I increase the pressure, equilibrium shifts to the right. If I decrease pressure, it's going to shift towards the larger number of moles. So it's going to shift to the left. Okay? Again, these are just some rules that you're just going to have to memorize and understand that this is what happens when we do these certain things to these types of reactions. All right, folks, so what am I going to ask you to do with this information? Well, it's very straightforward here. I'm just going to simply ask you which direction is the reaction going to shift? Am I going to increase my amount of products or increase the amount of my reactants based on this information here? So we have our equation up above. Kind of hard to see here, but we've got nitrogen, 3 hydrogens, and we're producing 2 NH3. I'm not worried about K. We'll worry about that another day. So if I add H2, let's look at the first one. We add H2. If I add H2, remember, adding something in my reactant side shifts equilibrium to my product side. So if I add H2, that's going to shift to the right, which means that the concentration of N is going to go down, and the concentration of NH3 is going to go up. Okay? What if we add some NH3? Well, if I add NH3, then equilibrium is going to shift the opposite direction. Okay? In order to compensate for the extra NH3 that's there, it's going to make more reactant. So we're going to shift to the left, and concentration of N2 is going to increase because equilibrium shifts to the left, and H2 is going to increase. Okay? Again, if we remove substances, it shifts the direction in which it is removed. So if I remove N2, equilibrium shifts to the left. So if I remove N2, equilibrium is going to shift to the left. H2 is then going to increase, and NH3 is going to decrease. Okay. If I remove H2, you have very, very similar outcome. If we remove H2, equilibrium is going to shift that direction to make up for whatever H2 is lost. So N2 is going to increase, equilibrium shifts to the left, and NH3 goes down. If we remove some NH3, the opposite happens. We're going to get it shift to the right because it's going to compensate for the NH3 that's lost. So in that case, N2 is going to go down, H2 is going to go down because we're reacting more to the right here, and equilibrium shifts to the right. Okay. So let's look at temperature. Well, this here, based on this information here, is an exothermic reaction. So we want to think of heat like a product. So if I increase the temperature, if I add more here, equilibrium is going to shift to the left. Again, we treat it just like we do with moles. So that means that N2 is going to increase, H2 increase, NH3 decrease. We decrease the temperature. So the opposite's going to happen here, right? Equilibrium is going to shift to the right. And as a result, we're going to see N2 decrease, H2 decrease, and NH3 increases. We make more product when equilibrium shifts to the right. Pressure. Remember, with pressure, we look at moles. So we got 4 moles total. We know that because we got 1 and 3 here. 2 moles on the right. If we increase pressure, equilibrium shifts towards lower number of moles. So we're going to shift to the right, which means I'm going to get more NH3, less N2, and less H2. And then when we decrease pressure, it's going to be the exact opposite. Okay. So again, it's just about finding those trends and understanding that when we lose something, when we gain something, it's all about trying to get things back into balance. And that's going to tell you which direction equilibrium is going to shift as a result. All right, let's move on. A few more things I want to take a look at here, just kind of before we finish things up. Changing volume. So you may get some questions about changing volume. Well, remember that volume and pressure are related, right? Volume and pressure are inversely proportional, or indirectly. So that means as one goes up, the other goes down. So if volume increases, pressure decreases. And then you can think about the pressure rule when it applies to Le Chatelier's principle. Catalysts only change the speed of the rates and therefore actually have no change on the equilibrium value. So if I add a catalyst, there's no equilibrium shift. And same thing if I add materials that are not used in the reaction. Adding materials not used in the reaction simply just has no effect. That's Le Chatelier's principle in a nutshell, guys, okay? Read it very carefully. Go through some practice problems. We'll review in class, and we'll see you guys next time. Have a great day, guys. We'll talk to you later. Bye-bye.